Okay, hello everybody. So, before we get started, I would like to start by saying thank you so much for all of the support that I've been getting from everybody. It means so much to me when I, hear people or I get comments from people saying, your videos are helping me and thank you for doing what you're doing. That makes it all worthwhile and really inspires me to keep doing this. So thank you very much. Certainly never thought that this would kind of take off the way it has. Um, and right now, those of you, who know me, right, and you know where I work, right? I work in Florida, and we do have the hurricane going on right now. So it's not very bad where I am right now. I'm in Gainesville. They did force us to, not go into work today, so I am home and kind of bored right now. And I did bring my computer home, and I thought, oh, this is a perfect opportunity to, put up some content for the channel. So that's exactly what I'm doing. And what we're going to talk about today is something that has been requested for a while. Okay, and this actually goes back to the video that I did a couple of years ago about zone axis alignment. Okay, and the question being, well, okay, so you're talking about the importance of aligning to the zone axis, but how do you know what the zone axis is, right? In that example for that video, I said this was a 110 family zone axis for silicon. How do you know what it is, okay? So this gets us into what we call indexing the diffraction pattern. I'm gonna get out of this for just a second here. Okay, so see this little, see if I can move this. Okay, I can move it. The little meeting controls here. Sorry, let me get this out of the way. Okay, so now it's not blocking it. Okay, there we go. Okay, so yes, so we're going to talk about indexing, or otherwise known as solving, a single crystal diffraction pattern. Okay, so when we talk about indexing a diffraction pattern, we're talking about two things. We're talking about figuring out the crystallographic zone axis along which the beam is traveling that is giving us this diffraction pattern. And we're also talking about assigning indices to all of the spots in the diffraction pattern. So by convention, we define the direct beam as our origin of the diffraction pattern. And so we always assign the indices as 000 for the diffraction pattern. Now, if we're working with a hexagonal crystal, we would use 4 indices. We're not going to talk about that in this video, okay? But yes, so that would be a specific example where we would deviate from that. Otherwise, we'd be using 3 index notation, okay? And so we define the origin as 000 being the direct beam, and then we can draw vectors from the direct beam to any of the spots, and we call those G vectors, okay? And so by convention, right, your vector originates from the direct beam and it points to a spot, okay? And so each of these spots have indices associated with them, HKL indices, because they are associated with Bragg diffraction from the HKL set of planes. And so we want to figure out what those indices are for the spots, okay? All right. There we go. Okay. So to index a diffraction pattern, okay, this is the process. So we have to find 2 spots that are perpendicular, okay, if that's possible, okay? And we want to find the shortest possible pair of G vectors that are perpendicular, okay? And so then we have to figure out the HKL family for each of those spots. And the way we do that is by measuring the relative lengths of the G vectors, okay? So how long is G1 relative to G2, okay? And this will work provided we already know what the crystal structure is to begin with, okay? So now I know there's a bunch of you out there right now that are probably saying, well, what if I don't know the crystal structure, okay? Very, very, very unlikely that you are going to be dealing with a scenario where you don't know what the structure is ahead of time, okay? Or you don't at least have some educated guesses as to what the structure is, okay? Very unlikely you're going to be, in a scenario like that. over the, time I've been doing this, right, many years now, better part of almost 2 decades, okay, I can tell you that the number of instances where I didn't already know the crystal structure ahead of time is very small, okay, although not to say that hasn't come up, right, because it has, okay, but the vast majority of the time you're already going to know the crystal structure, okay, and if that's the case, then all we need to do is measure the relative lengths of G1 and G2. Okay, so once we have potential families that meet the relative lengths, we then need to assign indices to G1 and G2 to satisfy a zero dot product, right? Because we stipulated that G1 and G2 are perpendicular, okay? So now when we put indices on the spots, this is a common error I see. You don't put any brackets or parentheses around the indices, okay? So if I go back here to the previous slide, okay, you can see, right, I didn't put anything around 000, okay? It's just 000. That is the correct notation for the spots in a diffraction pattern, okay? For the zone axis, you do want to put brackets around this, okay? So specific brackets, okay? And then after we determine the spots, right? So once we have 2 spots solved, we can solve any of these spots, okay? And the reason is the rest of these spots are simply the result of vector addition, okay? So, right, you can imagine this spot right here is the sum of G2 and G1, okay? This spot right here would be G1 minus G2, okay? So you can see, right, it's possible to get any of these other spots once I know 2 spots that are not a linear combination of one another. In other words, right, G2 is not simply a multiple of G1, okay? These are unique G vectors, okay? Okay, so once we have that satisfied, we want to determine the zone axis, okay? So by convention, the zone axis points out of the page, right, up toward the electron gun, okay? So you're looking at the diffraction pattern on your viewing screen or on your, your computer screen, right? The diffraction pattern is the out of page direction, okay? And so, right, G1 and G2 correspond to vectors in reciprocal space. So a neat consequence of computing the cross product of 2 reciprocal space vectors is you get out a real space vector, okay, which is B, okay? And then another thing that has to be satisfied is that I have to get a zero dot product with B and all of the G vectors that are in this Laue zone. Okay, as you can see, I have a ring here that contains all these spots. So this is what's called the zero order Laue zone, okay? And so all of the spots inside of the pattern, the indices must dot to 0 with B, okay? If we do everything correct. Okay, so now the zone axis, which was kind of the thing that, started all this, right? So we always define a diffraction pattern relative to a zone axis, okay? And the convention is, again, is that B points out of the page. So B is traveling the opposite direction that the beam travels, okay? So B points up toward the gun, okay? And again, B is a direction, okay? So you have to put these square brackets around it, okay? So there are some hard rules associated with B here, okay? So the hard rule is that you have to use the lowest magnitude integers possible for B. So in other words, we wouldn't use 336 bar, okay? We would use 112 bar. And now a blanket apology here. I did not go through and meticulously write little bars over all the indices, okay? Because that would have been a pain to do, okay? So this is, you should use bar notation here, okay? I'm not doing that for, purposes of simplicity, okay? But that's what you should do, okay? But I will call this as 112 bar, right? As how it should be indicated, okay? So 112 bar is correct, not 336 bar or 224 bar, okay? Because these are linear multiples of 112 bar. What we can do from there, though, is if we wanted to apply a soft rule, okay? If the material has a cubic symmetry, which is what we're going to be dealing with today, okay, in this tutorial, then we can apply some soft rules, okay? And so then we can rearrange the indices to minimize the use of negatives, okay? So in other words, if we're computing the zone axis to be 1 bar 1 0, we can remove the negative and call it 1 1 0, okay? Because those are equivalent and in the same family for a cubic crystal, okay? And then the other soft rule is we list the indices in increasing magnitude. So we wouldn't put 2 0 1, we would use 0 1 2, okay? Again, assuming the material is cubic. Those would be in the same family, okay? And again, these are the soft rules, okay? If we apply the soft rules and we rearrange the zone axis indices, we will then have to go and do some rearranging to G1 and G2, okay, as well. So, and we'll get into all of this here. We're going to do a bunch of examples here, so hopefully we'll give you plenty to chew on here, okay? All right, so, okay. So now what I mentioned was that all we need to do is compute the relative G vector lengths, okay? Because we are assuming we already know the structure, okay? When you record a diffraction pattern, it's going to have a scale bar, okay? And that scale bar will be in reciprocal length units. And if the person managing your microscope is doing his or her job properly, that scale bar should be accurate and calibrated, okay? Those of you who are using any of my microscopes, I assure you that when you are recording diffraction patterns using the calibrated camera, okay? So this is not using the FluCam viewer, okay? This is using the SATA cameras, okay? Or on the Techni, you're using the Gatan camera, okay? You are getting calibrated scale bars when you record the patterns, okay? But we don't even need to know that information in order to index the pattern, okay? All that really matters is the relative lengths, okay, of G1 and G2, okay? So there's no need to have a calibrated scale bar to do this. So the nice thing about a cubic crystal is that we can define the relative length of G as simply the summation of the squares of the indices H, K, and L, and then the square root of that sum, okay? So that's all we have to do to compute a relative, to compute the G vector length, okay, for a cubic crystal. And again, you don't see a lattice constant here because this is a relative G vector length, okay? So the lattice constant is irrelevant, okay? All we need to know are the indices, okay? So again, right, what we're going to measure in the pattern is actually a physical distance, okay? So like millimeters or inches or, you know, kilometers, right? Haha, right? You probably wouldn't be measuring kilometers, but we're going to be measuring a physical distance in the pattern, which is R, okay? So R is going to be the distance that we measure. We'll say, I think when I do this in PowerPoint, it's going to give us inches, okay? So we'll say this is, you know, this is R in some number of inches, and this is R in some number of inches for G vector 1 and G vector 2, okay? So the ratio of R1 to R2 is equal to the ratio of G1 to G2, okay? All right, so we'll go to the next slide here. Okay, so again, this is what we're doing, right? This is the real space picture. We're assuming we have a sample, which is a foil, okay? It's, you know, infinite in X and Y direction, and it's traveling along the thin direction, which is Z, okay? And we have it aligned intentionally near a specific zone axis, okay? Again, so Z, right, would point parallel to B and anti-parallel to the beam direction. Okay, so if we're dealing with a cubic crystal, the dot product for two orthogonal G vectors is very easy, okay? So it's simply H1 times H2 plus K1 times K2 plus L1 times L2 equals 0, okay? Standard dot product formula, okay? Things get more complicated if we're dealing with a non-cubic crystal, which could be, you know, a video in and of itself entirely, which we're not going to deal with today. We're going to assume that we have a cubic crystal just to make things easier to start with. And then we also have a very nice parallelism, okay? So because the material is cubic, the GHKL reciprocal space vector is always going to be parallel to the HKL real space direction, okay? So this makes it very easy to apply the different rules and to rearrange indices because we have this, this nice parallelism, okay? Because we're dealing with a cubic crystal. All right, so next slide here. Okay, so the first thing we're going to start with is some really easy stuff. Okay, so we're going to start by considering some very high symmetry zone axes for cubic. Okay, and those are going to be zone axes in the family 0, 0, 1, and 1, 1, 1. Okay, and again, any direction in this family would apply. Okay, so 0, 1 bar 0 would be in this family. 1 bar 1 bar 1 would be in this family. Okay, and these are actually very common zone axes that we typically deal with cubic materials. And these are nice because we can actually very quickly recognize the zone axis family simply by the point symmetry of the diffraction pattern, okay? So we're going to actually see some examples of this. And now what you're going to see are actually simulated diffraction patterns, okay? And what I did when I ran these simulations is I kept the lattice constant of the material the same. I kept the magnification of the pattern the same, the wavelength of the electrons the same, and the zone axis the same, but I'm changing the crystal structure, okay? So I'm going from simple cubic to body center cubic to face center cubic and to diamond cubic, but I'm keeping the lattice constant the same, okay? So what we can see as a result of this is that we will tend to get some changes to the appearance of the pattern, okay? And namely, we're going to see spots some of the time, not all the time necessarily, but some of the time actually disappear, okay, from our patterns. Okay, so if we're dealing with the 001 family to begin with, the arrangement of the spots has point symmetry 4 mm. Okay, so what this looks like is I have a four-fold rotational axis about the direct beam, and then I have 4 mirror planes that intersect the direct beam, and they're each rotated by 45 degrees relative to one another, okay? Now, one thing you have to keep in mind, though, you have to be careful with, okay, is that the symmetry that you see in the diffraction pattern is not always indicative of the true symmetry of the crystal, okay? So keep that in mind. You might look at that pattern and you might say, okay, I have four-fold rotational, I have point symmetry 4 mm for my material, so therefore my cubic crystal must have four-fold rotational symmetry, okay? That's not always the case, okay? So, keep that in mind, right? For instance, if I'm dealing with, say, a zinc blend cubic crystal, okay? Zinc blend does not have that symmetry operation, okay? So even though the pattern would indicate that it has, so even though the pattern has a certain symmetry, that is not actually representative of the true crystal symmetry always, okay? All right, so since we're assuming that we have a cubic crystal and we have 4 mm point symmetry, the indexing to do this is actually not terribly difficult, okay? So let's go to our first example here, okay? So our first example is, all right, so this is what a diffraction pattern with point symmetry, not an example yet, sorry. This is what a DP with point symmetry 4 mm looks like, okay? So if I add in the symmetry operators, right, I have four-fold rotational symmetry about the direct spot, and I have 4 different mirror planes, each one rotated 45 degrees relative to the other. Okay, so this is 4 mm point symmetry. Okay, so now here's our first example. Okay, is simple cubic. So over on the right here, I have the list of allowed HKL reflections for cubic crystals. Okay, and I stopped the list here. Okay, I could have populated this to be as long as I wanted, but I stopped it at 222. Okay, based on these indices, I can then calculate the relative G vector length, right? H squared plus K squared plus L squared, and then I take the square root of that. So we can see as my indices get bigger, my G vector length gets bigger, okay? So we know the zone axis is the 0, 0, 1 family, okay? We know that based on the point symmetry, okay? So now we have to figure out what are the spots, okay? So we don't need to, now what you should be doing, okay, if you want to be careful, you should actually go and measure these and verify, even though it looks like these are equidistant, okay? What you should be doing is you should be verifying. Okay, you should actually be measuring and making sure that you have that. So why don't we go ahead, let's do this here for the sake of, whoops, where'd you go? Okay, there we go. Did it do this? Okay, swap back. All right. So let me go, where are we? Okay. Go to shape format. Okay, so I have the patterns nice and, rotated here. So the spots are up and down. You may not see that. The pattern may be rotated. Okay, so this is kind of an idealized sample. So our shortest G vector lengths, right, are this guy and this guy. Okay, so we want to verify that these are the same length. Okay, so what I'm going to do here is I'm going to measure actually 6 of these increments. Okay, and then divide that number by 6, because that's going to be more accurate than just measuring 1. Okay, so I'm going to put my start arrow there. I'm going to hold down shift to keep the arrow straight. Okay, and so I get 3.35 for R1. And I'm going to do the same thing for the vertical component, or the vertical G vector. Come on, what are we doing? Yeah, what's going on? There we go. Okay, so I get the exact same number. Okay, so I get 3.35 for G1, and I get 3.35 for G2. And if I divide it by 6, obviously those would be the same thing. Okay, so I verified that those are the same length. You should also, okay, I don't have a protractor on here. You should also verify that this is a 90-degree angle. Okay, you shouldn't just assume that this is 90 degrees. Okay, this is pretty easy to do with the 001 family patterns, but when we get into like the twofold rotational ones, it gets a little easier to not properly assess the angles sometimes. So again, you want to verify that this is 90 degrees, but rest assured that it is. Okay, so let's go back here to the table. Okay, so here's the table. So now we're going to start by assuming that G, because they're both in the same family, okay, they're the same length, so they have to be in the same family. We're going to start by assuming that G1 is in the 001 family, okay? So then the question is, so now G2 has to also be in that same family, okay? Because they're the same length, okay? So the question now is, can we assign indices to G1 and G2 so that I get a 0 dot product with them being in this family? Okay, and the answer, of course, is yes, right? I can do that very easily. Okay, so let me go ahead and copy this here. Okay, so one thing I could do, I could assign, and this is only one possibility, right? I could assign that guy to be 1, 0, 0, and I could assign this guy to be 0, 1, 0. Okay, those both dot to 0. Okay, and I satisfy the orthogonality, right, that I have with the G vectors. Okay, so then if I assign this as G1 and G2, I have to compute the cross product. Okay, so again, my zone axis points out of the page. So I'm going to do 1, 0, 0 cross 0, 1, 0. The answer to that, of course, is very easy. Okay, the answer to that would be Thought I copied this, but I didn't. Let me go over here for a second. Copy that. Okay, so the answer would be 0, 0, 1. Okay, right? And so now, if I want to index some of these other spots, it's just vector math. Okay, so this spot here would be 1, 1, 0. This spot over here is the opposite, so I just make the indices negative. Again, I would use bar notation, but again, that's kind of tricky to do with this, but that's what you should be doing. Let me make these a little smaller here. Okay, this is the opposite, so this would be a 0, 1 bar 0. I'm just going to do the 8 closest here. Okay, this is the sum of these two, so this is 1, 1 bar 0. This is the opposite, so this is 1 bar 1, 0. And then this guy over here is simply 1 bar 0, 0. Okay, and so I have solved the diffraction pattern. Okay, now again, right, this is only one possible solution to this. Okay, I could have, for instance, if I wanted to, okay, let me shorten these up again here. Okay, I could have, if I wanted to, I could have assigned this as okay, and that would also be perfectly valid. Okay, that would be perfectly valid way. So I could have assigned this spot as 0, 1 bar 0, and this spot as 1 bar 0, 0. Okay, so if I do the cross product here, let me switch to MATLAB here. So we're going to do b equals cross, sorry, 1 equals 0 minus 1, 0. G2 equals minus 1, 0, 0. And then B equals cross G1, G2, right? Because we want the out of page direction. Display B. Okay. So yes, so it gives me now the zone axis would be 0, 0, 1 bar. Okay. And now the other thing we have to keep in mind, again, if we index it like this, okay. Now the other thing we have to keep in mind is we have to satisfy G dot B is 0 for all the spots here in the 0 order Laue zone. Okay. So you can see very clearly for 0, 0, 1 here that that is indeed the case, right? I get a 0 dot product for all of these indices here. Okay, and now when we picked the indices, we ended up correctly assigning B so that we don't have to apply the soft rules, okay? Because this is exactly what we would get for B if we applied the soft rules, right? So if we got the answer to be 0, 0, 1 bar, okay, then that would have to be reduced down to 0, 0, 1 if we apply the soft rules, okay? Because right, we wouldn't want a negative there, okay? And if we did that, right, we would have had to reassign G1 and G2 to account for that change, okay? So now a good question to ask here is, okay, I'm telling you that these two closest spots are in the 001 HKL family, okay? I could just as easily though, okay, if we go down to the next family, 011 family, I can also assign two G vectors, okay? for this family that would also dot to 0. Okay, I could also do that. Okay, so you might be saying, well, how do you know that these two closest spots are this, right? And how do you know that they, for instance, aren't instead? How do you know that they aren't like this? Okay, so instead of, okay, so how do you know that we don't have 1, 1, 0 for G1 and 1 bar 1, 0 for G2? Okay, so the reason for that is, right, if I do the vector math here, okay, so let's say I add the spot over here, right? What I would be getting if I added these two, I would be getting, okay, I would be getting 0 to 0, right, for this spot right here, okay? And then right here, between 0, 0, 1 and 0, 2, 0, I would be seeing 0, 1, 0 because it's a simple cubic crystal, okay? And that's allowed. But if you look at the pattern, we don't see a spot there, okay? There's no spot there, right? So if there's no spot there that can be indexed as 0, 0, 1, okay, then this isn't then the correct indices for this wouldn't be 1, 1, 0 family. Okay, so that's why these, even though we could get them to dot to 0 with a 0, 1, 1 family HKL, that is why that would not be correct. Okay, because we are missing the spot here that would correspond to the 0, 0, 1 family. Okay, if those were that family. Okay, so again, right, there's only one combination that works and that actually is consistent with the appearance of the spots. Okay, whoops. Okay, all right, so there we go. I'm going to go ahead and copy these for the next example, which is going to be body-centered cubic for the same zone axis family. Okay, so now we have a body-centered cubic crystal. Oops. Let me deselect this. Okay, and now once again, you should measure the spots and verify that you have them the same length. Okay, and you should verify that they are orthogonal. Okay, I'm not going to do that. You can take my word for it that this is true. Okay, and I assure you that it is. Okay, so now my shortest G vectors are here and here. Okay, so now we can do the same exercise that we did before. So here's my allowed HKL, and this is my relative G vector magnitude. Okay, so now if you look at this list for body-centered cubic compared to simple cubic, you can see we're now missing some of the reflections from simple cubic. Okay, so there's no 0, 0, 1 anymore. That's gone. Okay, there's also no 1, 1, 1. That's also gone. Okay, so without going into too much detail here, the rules for body-centered cubic for allowed reflections are that the sum of your indices has to be an even number. Okay, so if you add up all of the indices for any of these reflections in the list, you will see that those add to an even number. Okay, that is the rule for body-centered cubic. Okay, so we'll start by assuming, right, that here's my shortest G, and this is my orthogonal, which is also the same length. Let's start by assuming that this is in the 0, 1, 1 family. Okay, so once again, let me delete some of these to avoid little confusion here. So again, can we assign indices to both of these spots to get a 0 dot product? Okay, and the answer, of course, is yes. Okay, so let's, for the sake of argument here, sorry, I'm going to put this as a question mark yet because we haven't solved the zone axis. Let's say, to make this a little trickier, let's say that we're assigning G1 as 0, 1, 1. Okay, so then what are our indices for this other guy? Okay, Well, the easiest answer, I was going to say 1, 0, 0, but that wouldn't be consistent, right? It has to be in this family. Okay, so let's do 0, 1 bar, 1. Okay, that gets me a 0 dot product. Whoops, sorry. Okay, and let's put this here. Okay, so we have a 0 dot product. So now we need to compute the out of page direction. So that would be 0, 1, 1 cross 0, 1 bar, 1. Okay, so let me go back to MATLAB here really quick. We have 0, 1, 1 cross 0, 1 bar, 1. Let me make sure that that's actually correct. 0, 1, 1, 0, 1 bar, 1. Yep. Okay, so it's giving me the answer is 2, 0, 0. Now this we need to reduce down. Okay, we need to reduce this down to 1, 0, 0. Okay, so our answer in this case would be 1, 0, 0. Okay, and then let's do the vector math here. Sorry, I'm jumping ahead here. Let's do the vector math here for these 8 closest spots. Okay, so now I add these two G vectors and I get 0, 0, 2. Okay, this is simply the opposite. This is the opposite as well. Oops. Okay, this spot up here is the sum of these two. Okay, so I end up now with 0, 2 bar, 0. And now this is 0, 2, 0. And this guy over here is 0, 1, 1 bar. Okay. And again, as a sanity check, right, we add these two together. Yep, we get 0, 0, 2 bar. Okay. And then you could finish the rest of these off the same way. I do have a 0 dot product between B and all of these indices. So we're good. Okay. Now, if we wanted to apply the soft rules, okay, if we wanted to apply the soft rules, we would rearrange this as 0, 0, 1. Okay. So now what we have to do is we have to reassign indices to these two spots such that I get a 0 dot product, because right now I'm not going to get that. Okay. So I could call this one 1, 1, 0. Okay. So now I need to figure out what my indices are for this one. Okay. So B is my out of page direction and my other G vector is this. If I do B cross 1, 1, 0, my result is going to point here. Okay. And again, right, because I have this parallelism between real and reciprocal space for a cubic crystal, that should give me the answer here. Okay. So I'm going to do 0, 0, 1 cross 1, 1, 0. Okay. So let's go back to MATLAB here. 0, 0, 1 cross 1, 1, 0. Okay, and so I get 1 bar, 1, 0. Okay, and so now, right, I can re-index the rest of these spots. Okay, so now this one becomes 0, 2, 0. Oops, I'm just going to delete these. Okay, that's the opposite. Okay, that's the opposite of that. Oh, whoops. I did a little math wrong here. Okay, this should be, my bad. Glad I caught this. This should be minus 2, 0. Okay. Should be minus, this should be 2, 0, 0. Yep, that's correct. Okay. Glad I caught that. Then we switch the indices there. Okay, so that's my solution. Okay, if I apply the soft rules. Now, I could have assigned any of these. So once I stipulated the zone axis was 0, 0, 1, I could have assigned any of these 4 closest spots to be 1, 1, 0, and I would have got the exact same answer. Okay, the only difference is that answer would have been rotated relative to the answer you're seeing here. Okay, but I could have just re-rotated the pattern back and got it back exactly as it is here, right? So you can imagine I could take this whole pattern and I could rotate it 90 degrees, okay? It's going to be the exact same pattern, right? The only thing that would change if I say assigned this spot here to have been 1, 1, 0 initially, again, would be just that the pattern would be rotated counterclockwise by 90 degrees relative to where it is now, okay? But it would be otherwise identical. All right, so that's body center cubic. Let's go to face center cubic. Okay, so now look what's happening here. Okay, as we go from body center cubic, face center cubic, I'm losing spots in the pattern. Okay, so generally speaking, right, as you add more atoms to the unit cell, this is what tends to happen, right? So you can see our HKL list is, now this is obviously, I'm stopping here at 1, 3, 3, but you could extend this out further, okay, if you wanted to. I'm only stopping here because I know I don't need to go longer than that, okay? But you can see what's happening, right? I'm keeping the unit cell the same in terms of its lattice constant. I'm just changing the structure, okay, from body centered to face centered, okay? So those spots that were here, right, are now gone, okay? Again, you can take my word for it, right? I have 4 mm symmetry. These are perpendicular, and these are the same length, okay? I'm not going to measure it. You can go ahead and do that yourselves. Okay, so let's go ahead here, and let's grab, come on. Come on. Okay. All right. So we know that's 0, 0, 0, okay? So now we'll start by assuming that the G vectors are in the 1, 1, 1 family, okay? So first question, can we assign indices to 2 1, 1, 1 G vectors that I get a 0 dot product? Okay, answer is no. Okay, it's not mathematically possible. Okay, you can do it yourselves and prove it. Okay, but that's not mathematically possible. If I go down to the next family, though, this is very, very, very possible. Okay, so again, right, I could assign exactly the same indices. Whoops, I could assign the exact same indices that I had here for the body-centered cubic for these spots. Okay, so I could assign this as 0, 2, 0 and 2 bar 0, 0. Okay, and again, right, because we already know, because we just did the cross products, okay, I would end up with the same answer here. Okay, to make this a little more interesting, though, okay, let's start by assuming that my zone axis is actually, let's do 0, 2, 0, and let's do 0, 0, 2 bar. Okay, now these dot to 0. So now let's do the dot. Let's do the cross product. So we have 0, 0, 2 bar and 0, 2, 0. 0, 0, 2 bar, 0, 2, 0. Okay, so I end up with 4, 0, 0, which reduces down to 1, 0, 0. Okay, and then we can do the vector math here. It's my opposite. That's my opposite. This is now 0 to 2. Oops, sorry. And this is 0, 2 bar, 2 bar. Okay, and now this spot up here is 0, 2, I'm sorry, 0, 2, 2 bar. And then this spot back here, down here and to the left, I should say, in the southwest corner, 0, 2 bar, 2. All right, and so we have solved this now for this being B as 1, 0, 0. Now again, right, the same reason why I talked about for the simple cubic, we cannot assign these closest spots to be 0, 2, 2 family. Okay, the reason being, right, if that was the case, we would see, okay, we would see right here a spot if that was the case, and we don't. Okay, we don't see a spot here that would correspond to 0, 0, 2. Okay, so for that reason, right, this is why, you know, you start by considering the shortest G vector and you move up from there. Okay, so yes, so this is correct as the 0, 0, 2 family and not 0, 2, 2 family. Okay, again, because we are missing a spot here that would otherwise be there. Okay, and again, right, we showed how before, if we wanted to do this, because we just happened to pick the right indices, right, to get the soft rules if we wanted to put this at 0, 0, 1. Okay, I'm going to go ahead and leave it at 1, 1, 0 though. All right, so let's move now to diamond cubic. Okay, now look again, right? Face-centered diamond, face-centered diamond. Okay, I'm losing more spots. Okay, so the rule with face-centered cubic is that your indices have to be either all odd or all even. We call that unmixed. Okay, and so diamond cubic is basically an extension of face-centered cubic. The only added stipulation has to do with if you have even indices. Okay, if you have even indices, the sum has to be a multiple of 4. Okay, so you'll see here in diamond cubic there isn't 0, 0, 2 family, there isn't 0, 0, 6 family, there isn't 2, 2, 2 family. Okay, those are all forbidden. Okay, all right, let me go ahead and copy some of these again. Oops. Let me copy it from the face-centered one, because I think you can imagine where we're probably going with this. Okay, so let's go ahead and... Okay, so we know 1, 1, 1 won't work, but 0, 2, 2 will. Okay, so let's go ahead and assign this spot. Let's call it 2, 2, 0, and we'll call this one 2 bar 2, 0. Okay, so now 2, 2, 0 cross 2 bar 2, 0 gives us the out of page direction. Yep, that's right. Okay, so I end up with 0, 0, 8, which reduces down to 0, 0, 1. Okay, so again, I happen to very coincidentally pick these so I get these soft rules already applied. Okay, again, if we do the math here, okay, so I end up with 0, 4, 0. Okay, that's 2 bar, 0. Okay, this is going to be 4 bar, 0. This spot down here will be 4, 0. And the last spot here that we'll index over here, this will be 2 bar, 0. Okay, now notice also, okay, and you can do the sanity check, right? So this is 4, 0, 0, 0, 4, 0, x cross y gives us z. Okay, now also if you're doing this correctly, your equidistant spots should all be in the same family. Okay, as you can see, right, these are all equidistant, they're all in the same family, 0, 0, 4 family. Okay, just like these are all equidistant and they're in the same family. We can go back here and look at the face-centered cubic, and we have the same thing. Okay, the same thing here for the body-centered, right? And the same thing here for the simple cubic. Okay, again, if you're indexing these correctly. Okay, so again, we happen to pick these so we get the soft rules applied. So let's just say, for the sake of argument, that instead of indexing it like this, let's say we want to index it as let me see here. Move these. Well, they're already kind of not in the way. Okay, I'll leave this here. Let me say, let's say for the sake of argument, we want to call this 0, 2 bar 2. Okay. What do we want to assign for this one? Well, we can assign this as 0, 2, 2, and that will give me a 0 dot product. Okay, so now I have to do 0, 2 bar 2 cross 0, 2, 2 to give me B. And I get 1 bar 0, 0 as my zone axis now. Okay, again, assuming I assign these differently. Okay, so now I can rearrange this and I get 0, 0, 4. And then this becomes 0, 0, 4 bar. And then this becomes 0, 2, 2 bar. And then this becomes 0, 4, 0. And then this becomes 0, 2 bar, 2 bar. And this becomes 0, 4 bar, 0. Okay, so this would again be another perfectly valid solution to this, okay, where we're not applying the soft rules. Okay, so if we started from this, we could get this, and then we showed how we could rearrange these if we wanted to. Now again, if we wanted to stipulate that this was 0, 0, 1, okay, now we have to rearrange indices here. Okay, so we could call this one 2, 2, 0, okay, and then B cross 2, 2, 0 is going to point at this spot. Okay, so we can do this now as 1, okay, something B cross 2, 2, 0, 1 cross. Oh, sorry, I did this wrong. No, I don't want 1, 0, 0. I want 0, 0, 1. There we go. Okay, so we get 2 bar 2, 0 here. Okay, and then again, right, you'd have to rearrange the rest of these spots. I'm not going to go ahead and do that. Let me go ahead and erase these though. Okay, and again, this is if we want to apply these soft rules. Okay, if we don't want to index this as, say, 1 bar 0, 0, and we want to index it as 0, 0, 1. All right, so that is the end of the 0, 0, 1 family zone axes, and now we're going to go on to the 1, 1, 1 family of zone axes. Okay, And so again, the process here is very similar, okay? But the point symmetry of the patterns is different, okay? So what we now have is a point symmetry called 6mm. So we have 6-fold rotational axis about the direct spot, and then we have 6 intersecting mirror planes that are 30 degrees relative to each other, okay? All right, so if we again, I'm not going to show a simple cubic example. We're just going to go straight to body centered, okay? So now our orthogonal G vectors are no longer equidistant, okay? So if we look here, right, this is the closest to orthogonal G vectors, okay? Or I could do this one, right? That's the same thing, or I could do that one. This is easiest though, because you know it's oriented up and down, okay? But my G1 and G2 are no longer the same length, okay? So now it's not as simple as it was before, where we knew that the G1 and G2 had to be in the same family. Now G1 and G2 can't be in the same family, right? They can't be in the same family because we have a difference in the lengths, okay? All right, so let's start here by, so which, it doesn't really matter which G vector you make be the longer one or the shorter one. You should end up with the same answer. I tend to prefer to make G1 the shorter vector, okay? And I tend to prefer to make G2 the longer one. I also tend to try and arrange them so G2 cross G1 gives us B, but you don't have to do that, you know, strictly speaking. So if we're going to do that, why don't we call, just for the sake of argument here, I'm going to call this guy G1 right here, okay? So again, there's 6 increments there. So let's measure 6 increments. So I'll put my arrow starting there. Let me scroll down. Okay, right there. Okay, and now I only have 2 here that I can use for G2, so we'll have to make do with that. Okay, so okay, so let me move this guy out of the way here because it's a little in the way right now. Okay, so if I go to my shape format here, okay, so my G2 R value is going to be 2.74 divided by 2. Okay, let me go ahead back to MATLAB here. Okay, so I have R1, or sorry, R2 equals 2.74 divided by 2, and my R1 is this guy, and that is going to be 4.74 divided by 6. Okay, so now if I do R1 divided by R2, what do I get? I get a ratio of 0.5766. Okay, so not exactly. So one of them is a little bit more than half the length of the other one. Okay. Okay. So what we do now, and again, this is a little trickier because now we don't have the luxury of them being in the same family. Okay. What we do though is we start with the assumption that G1 is in the HKL family. Okay. Then what we do is we divide all of these other numbers here by the ratio that we measured, okay, by the 0.577. Okay, we can round it up to 0.577, okay? Okay, so we divide each of these numbers through by that ratio, okay? And then we want to see if we end up, oh, sorry, we want to, hold on a second here. Okay, no, my bad, okay. All right, so we have the measured ratio, okay? What we want to do now is we want to start with the assumption that G1 is in the 0, 1, 1 family, okay? So then what we're going to do is we're going to take the relative length of that G vector, which in this case is 1.414, and we're going to divide that length, okay? We're going to take that length and we're going to divide it by the other G vector lengths, okay? So then obviously if we do 1.414 divided by 1.414, we get 1, okay? Then if we do 1.414 divided by 2, that's less than 1, and then the number is going to keep decreasing from 1, and it's going to continue to, get smaller as we go down the table, okay? And then we're going to look and see if there's any matches with the experimental ratio, okay? If we don't find a match, okay, then what we're going to do is we're going to go to the next G vector. So we're going to then assume that G1 is the 0 to 2, okay? And we're going to then go through and do the same thing. So we're going to divide each of these by 2. And hi, my family just came in here, so say hi to them while I'm doing the video. So we're going to then assume that the G vector is in the 0, 2, 2 family and do the same thing. Okay, so we'd go through this list, divide all of them by 2, and see if we have any matches with the ratio. We do the same thing for the third, right? And again, so we'd go through the list, divide by 2.45, and see if we have anything close, okay? And we want to see, again, not only if we get anything close, but if we get a close match, we want to see if we can mathematically get the two G vectors to dot to 0, okay? So I have MATLAB open here. I wrote a little bit of code to do this, okay, to make this easier. So basically, I wrote code that is going to go through and it's going to generate a table where I have this G vector list divided through by each of these lengths. So I'm going to have one column that has this list divided through by this first number, and then another column that has the list divided through by the second number, and then another column that has it divided through by the third number, and so on and so forth, okay? And then we're going to see if we have any close matches, okay? So let me switch over to MATLAB here, okay? So the only thing we have to tell the system here is we have to tell it the measured distance for D1, okay? So I measured 4.74, and our number of increments was 6. Okay, and then for the second one, I measured 2.74, and my number of increments was 2. Okay, and then I have to tell the system that we have a body-centered cubic crystal, and then we have to tell it to use the relative G vector lengths for body-centered cubic. So basically, I already have here in the code, I have tabulated values for simple cubic, body-centered cubic, face-centered, and diamond cubic, okay? And so this is all we have to tell the system, and then I can run the script here, and we should get out some results here, okay? So we'll do dp solve cubic. Whoops. And it's barking at me. All right, so let's see what's wrong here. BCC, body-centered cubic. Okay. Duh. All right. There we go. Okay. So let me expand this here. Okay. So our measured ratio G1 by G2 is 0.577. And so here's the table. Okay, so it's the G vector list divided through by the first G vector, the G vector list divided through by the second, and then the list divided through by the third, and so on and so forth. Okay, so you can extend this list out as long as you want, depending on how many G vectors you have in your list. Okay, so I stopped it at, how many is there here? I think there's 1, 2, 3, 4. I think there's 13 here. Let me go back here and see, because I'm actually curious. Genome, what do we have here? Oh, well, it says here it's 12. Okay, so yeah, so we have 12, 12 vectors here in the list. Is it 12? Yeah, it is 12. Okay, all right, so what we're doing now, okay, we have our measured ratio. We want to find in the table, okay, the close values. So there's one right here, okay, there's one right here. This one's a little too far off, so we're going to neglect that. There's one right here. This one, again, is, off enough. And then there's one more right here. And then really nowhere else in the rest of these columns is there a close match, okay? So now, in this first hit right here, okay? So this is telling us that I have a match, assuming that G1 is the first G vector in the list, and G2 is the third G vector in the list, okay? The hit that I have here in the second column is telling me that G1 could be the second G vector in the list and the sixth, okay? And then for the third column, it's telling me G1 could be the third vector and then the ninth G vector in the list. And then the last one is telling me that G1 could be the fourth G vector and the 12th G vector in the list, okay? So I then had to go through the HKL list and actually tabulate this so we don't have to go and figure it out, okay? So these are the potential pairs, okay? So we have 0, 1, 1 and 1, 1, 2 family, okay? And then we have 0, 0, 2 and 2, 2, 2 family. And then we have 1, 1, 2, 0, 3, 3 family. And then we have 0, 2, 2, 2, 2, 4 family. Okay. All right. So the question is then, can we get any of these to work? Okay. So yes, we can get this first one to mathematically work. Okay. That one would work. The second one will not. The fourth one here is actually a linear multiple of the first, okay? So we can just neglect this. This is actually just the same as the first result, okay? So now this third one is a little bit interesting, okay? Because this is the, it looks like it's a reverse of the first two, right? With this being a linear multiple of the first G vector, okay? So really our possible answers are this first one and the second one, okay? So then we can, let's assume then, if we're dealing with the first one, that we have, well, actually, for the sake of argument here, let's assume it's this second one here first, because I know this is not the right answer, and I want to show you why, okay? So let's assume that our first HKL is 112, just for this, make this easy. Okay, so let me go ahead here. I'm gonna move these out of the way for a second. Okay, so here's G1. That's 112. And then this spot right here has to be a 0, 3, 3 family that dots the 0. So I could call this 3 bar 3 0, and that will work. Okay. All right. So now the vector math works, but the arrangement of the spots has to also work. Okay. So if I add 112 to 3 bar 3 0, okay, and I get this spot up here in the corner. Okay, what do I end up getting? I end up getting 2 bar 4 2, okay, which would be allowed. Okay, so there's no problem there. Okay, and then this spot right here would be 1 2 1. Okay, but the problem is, okay, I should have, right? A 0, 1, 1 spot and a 0, 2, 2 spot. Okay, if this is 3 bar 3 0, there should be a 2 bar 2 0 spot and a 1 bar 1 0 spot, and they aren't there. Okay, so because I don't see those spots, even though the vector math works, it's not consistent with the spot patterns. Okay, and because of that, I can know then that this is not the solution. Okay, which is why I did it first. Okay, so the correct answer is this one. Okay, so let's actually, we'll rewrite this as 1, 0, 0, and we'll rewrite the second one over here as, so you can see, right, with the threefold, this is a little more involved than with the 0, 0, 1 family. Okay. All right. So now we want to compute the zone axis here. Okay. So, so if we do 1 bar 1 2 cross 1 1 0. Okay. So I have another script right here. One bar 1 2 cross 1 1 0. So this script should actually reduce the indices for us and not just give us out a multiple here. So we do B solve. Okay, so it's telling us the zone axis is 1 bar 1 1 bar. Okay, just like we were expecting, right? It should be in that zone axis family, okay, because it has that point symmetry. Okay, so let me come back here. One bar, 1 1 bar. Whoops. That's what I got here, right? Yes. Okay, so from here, it's again simply a matter of vector math. Okay, so now all of these spots that are equidistant should be 1 1 0 family. Okay, if we do the math right. Okay, so what do we end up with out here? And now these spots, these are just a doubling of these, right? So these should all be basically just doubled indices, right? So this guy out here is going to be 2 2 0. Sorry, 2 2 0. Okay. This spot right here, this is 0 2 2. And then, right, I should see a 1 1 0 family spot halfway between, which I do. Okay, so that's how we know this is the right solution. Okay, and then if I want, so this spot is going to be the opposite. This spot is going to be 2 0 2, 2 bar 0 2. This spot is 1 bar 0 1. Okay, I'll index a few more of these, but you get the idea. 1 0 1 bar. This is the opposite. 1 0 1 bar 1. And this spot here is so now this is not going to be in the same family. This should be in a 1 1 2 family, right? So this is going to be -1, sorry, -1, -2, -1. Yes. Yes, that is correct. Okay. And then this one over here is the opposite. So that would be 1 2 1. Okay. And you can go on and do this, right? So all of these spots that are equidistant, those are going to be in the 1 1 2 family. Okay. All right. So now if we want to, now this is a valid solution for this pattern. Okay. Perfectly valid solution. If we want to apply the soft rules, okay, we would rearrange this as 1, 1, 1, okay? And now what we have to do is we have to, I'm going to move these guys out of the way here for a minute, okay? So we need to reassign indices to give 0 dot products now with these two spots, okay? And again, if we do G1 cross B, we're going to get G2, okay? So let's just call this 1, 1 bar 0, because that works, okay? So now I go back to MATLAB, and if I do, where are we here? I can do cross well, let me just write this. I think so. Cross 1, -1, 0. Okay, 1, 1, 1. Okay, and yes, it's giving me 1 bar, 1 bar, 2. Okay, yep, and that works out. Okay, and then from there, it's just doing the vector math, right? So I'll just do a couple of these spots. I'm not going to redo all of them here. Okay, so that is 0, 2 bar, 2. And that is 0, 1 bar, 1. Okay, and again, we see we have the 0 dot product between B and all of these spots in the 0 order Laue zone. Okay, all right, let me go ahead and I'll leave these here for now because we'll need them for the next example, I think. Okay, so we're going to go now to base center cubic, and look what happened. Okay, I lost more spots. Okay, I lost a lot of spots actually by changing my crystal structure. Okay, all right, so let me copy over some of these here. I'm going to copy this. I'll just copy those few there. Okay, so now, as you can probably guess, right, I have G1 here and G2 here, okay? I'm going to get the same ratio for R1 to R2, okay? I should, right? The symmetry is the same. The arrangement of the spots is the same, even though they're spaced out wider, but I should get the same answer, okay? But just for the sake of argument, let's go ahead and measure. Okay, so we have okay, so that's 3.16. So I'll go back to my solving pattern here. Okay, so I get 3.16, and that's 2 divisions. And then I have to do the same thing for G2. And now again, you could do this with G2 being smaller and G1 being shorter. You'll get the same answer. It will work both ways, I assure you, okay? And what do I have here? I have 5.47. Yep, 5.47. And I have 2 increments, okay? And then we have to tell the system now that our structure is FCC, okay? And let's go ahead and run dpsolve cubic. Okay, so our measured ratio, yep, basically the same as it was before. So if we go through the list, we really don't have a good hit here in the first column. We get 1 here in the second, which would say that G1 is equal to the second G vector in the list, and G2 would be equal to the 5th. And then we get another good hit here in the third. We really don't get anything close because the ratios are too big, okay? So this would again be G1 is the third G vector, and G2 is the last in the list. So there's actually 1, 2, 3, 1, 2, looks like 9 here. So if I do G-num, yeah, I have 9, okay? So this is a little easier here and then the last one. Okay, we only have two possibilities here, and the first one mathematically doesn't work. Okay, but the second one does, right? This will work perfectly fine here. Okay, so let's assign. And so actually you can see, right, these are actually just linear multiples of the answer we got for the body center cubic, right? All we're doing is multiplying these by 2, okay? If we do that, we should end up with the same exact answer here, okay? So we can assign this to be 2 bar 0, and we can assign this one to be 2 bar 4. Okay, and then we can do the math. This should give us 1, 1, 1, but let's do the math. So if we do 2 bar 4 cross 2 bar 0, okay. Okay, what do we get here? B, solve. Yes, so we get out that the zone axis is 1, 1, 1, just like we should, okay? And then, again, we can do the vector math. So actually, the spot's being covered up here. So let me do a different one here. Minus 2, 2, 0. And this would be 4 bar 0, 4 bar, right? Which makes sense. This is a linear multiple of this spot, so it should be basically just doubling the indices. Okay, 2 bar 0, 2 bar, 2, 0, 2 bar, 2, 2, 4 bar, and we'll do one more here. It's just the opposite of this guy. Okay, which is, oh, whoops, did I mess that up? I did. Yes, I messed something up here. No, this wasn't right. I was going to rewrite that as something. Yes, this should be the opposite here. So this should be, my apologies for that. That is correct there. This spot right here is 0, 4, 4 bar. And now we can't see it because it's covered up, but this spot out here is 0, 4 bar 4. And so this would be 0, 2 bar 2 right here. And so this is half of that. So we end up with 0, 2, 2 bar. Okay. So there's our solution, right? We can see these are all equidistant, right? And they're all in the same family. Okay. And the same thing with these right out here. These are all also equidistant and also in the same family. Same thing would be the case for these 0, 4, 4 family spots, which actually are outside of the G vector listing here, okay? All right, so that is the face center cubic, okay? If we go to diamond cubic, pattern looks the same, okay? So this is a rare instance where the zone axes for the two structures, even though the structures are different, the appearance of the patterns is the same, okay? So if we actually, we're going to get the same ratio, obviously, okay? So we don't need to go ahead and do the math. So we can index this literally identically to what we have here, okay? But for the sake of argument, rather than just reapplying this, why don't we instead, let's assume that we do it a little differently. So instead of assigning G1 as this, okay, so let's assume that let's assume instead that we are calling this spot 0, 2 bar 2. Okay, so then what does this spot have to be? Well, this spot could be 0, 4, or 4, sorry. This spot could be 4, 2, 2. Okay, that will give me a 0 dot product. So then what is my zone axis? I do 4, 2, 2 cross 0, 2 bar 2. Okay, let me go back to MATLAB. 4, 2, 2, 0, 2 bar 2. Okay, and we end up with, yes, right? We get an answer that's in the same family. 1, 1 bar, 1 bar. 1, 1 bar, 1 bar. Okay, and yep, we can verify that we get the dot products to work. Okay, so if we want to just index a few of these, zero, 2, 2 bar. These are all just the negatives. The last one. This is 4 bar, 0, 4 bar. All right, this is the opposite here. So 2, 0, 2. Oops. This is 4, 2, 0. Does that make sense? No, that shouldn't be right. 4, no, 4, 4, 0. 4, 4, 0. Okay, 2, 2, 0. And we'll just do a couple more here. 1, so that's 2 bar, 2 bar, 0. And then the last one, of course, out here will be 4 bar, 4 bar, 0. Okay, and so this would be a perfectly valid solution here. And again, if we wanted to apply the soft rules and index the zone axis as 1, 1, 1, this would be the solution. Okay, again, depending on how we how or where we assign G1 and G2, we should get the same arrangement between them, but the pattern may be rotated relative to the other pattern. But I assure you it is, there's only one unique, once you specify the zone axis, there's only one unique solution, okay? You can rotate that solution and change its orientation, but you're not changing the solution at all, okay? So once you specify the zone axis, you only have one unique solution. Okay, so we're going to kick it up a notch here for the last part of this, which is, sorry, just getting a drink here, which is cubic crystals where the DPs have 2 mm point symmetry, okay? And so this gets much harder because you cannot immediately identify the zone axis based on that point group symmetry, okay? Because there's basically an infinite number of zone axes that can have 2 mm point symmetry, okay? So you can no longer simply say it has 2 mm point symmetry, it therefore must be this zone axis, okay? It's not possible anymore, okay? But there are some that tend to come up pretty predominantly in terms of their technological relevance. One that is very important for face-centered cubic, zinc blended diamond cubic is the 0, 1, 1 zone axis, okay? I often tell people that the 0, 1, 1 zone axis of silicon is the most examined zone axis in TEM that has ever been done, okay? And it probably is, okay? All right, so solving the patterns and determining the zone axis is going to be a little bit more challenging now because we don't have the advantage of knowing what the zone axis family is from the beginning, okay? But we will soldier on here and do this anyway. Okay, so this is what 2mm point symmetry looks like, okay? I have two-fold rotational symmetry, and then I have two intersecting mirror planes that are orthogonal to one another. Okay, so here's my first example. So I have face-centered cubic, and I have 2mm point symmetry. Let me go ahead and copy some of these spots here so we have them. Okay, let me just put this off to the side for now. Okay, so first thing we got to do is measure G1 and G2. All right, so how about for the sake of argument, see that's G1. No, that's fine, we'll do that, okay? So that's G1 right there. So we have 3.87 and 4 divisions. Okay, so we end up with okay. And then if we do the same thing, we only have 2 divisions here. Okay, and we end up with 3.17 and 2 divisions. Okay, and we need to specify, yep, so we're specifying face-centered cubic. Okay, and let's see what we get here. Okay, dp solve cubic. Okay, so it's giving us 2 possible hits here. And the second hit we can throw away because mathematically it doesn't work, okay? So we really only have one possibility here, okay? And we can look at this and we can tell pretty quickly that yes, we can get this mathematically to dot to 0, okay? So let's assign G1 to be just 1, 1, 1 to make our lives easier. Okay, so let me get these out of the way here. Our little, whoops. Let me see if I can, yeah, to keep them locked there. Okay, so that is 1, 1, 1. So now I need to assign indices to this spot that are in the 0, 0, 2 family that gives me a 0 dot product. So the ones listed already work. Okay, so we'll just leave it right there. Okay, so now 1, 1, 1 cross 0, 2 bar 2 gives me B. Okay, so I come back to this guy. Now let me I'm going to rearrange this here since the order that I've been doing this, okay, just to make it easier for my brain. All right, so we'll do B solve. Yes, so it's telling me the zone axis is 2, 1 bar, 1 bar, okay? 2, 1 bar. Okay, so my zone axis family is the 1, 1, 2 family, okay? And this spot here, I'm just going to index the closest 8 again. So this would be 1, 1 bar, 3. This would be 1 bar, 1, 3 bar. This would be 1 bar, 1 bar, 1. This would be 0, 2, 2 bar. Oops. And this would be 1, 3, 1 bar. And then the last spot would be one bar, 3 bar, 1. Okay, so again, notice, right? My equidistant spots are in the same family, right? These are equidistant. They're both 1, 1, 1 family. These are both 0, 2, 2 family. And these other 4 are all 1, 1, 3 family. Okay, so now if we want to apply the soft rules, we're going to rewrite this as 1, 1, 2. Okay, so then let's rearrange this one to be, if we do, let's see. Okay, if we do 1, 1, 1 bar, that gives me a 0 dot product, okay, with B and G1. So then if I do B cross G1, I end up with this answer here. Let me delete the rest of these here. Well, I won't delete these yet, sorry. All right, so let me go back here. Okay, so I have 1, 2, 2, cross this. Yes. Okay. Now I have to reduce this down, of course. It just tells me the direction. So this is actually 2 bar to 0. Okay. So I end up with 2 bar to 0. Okay. And then I can rearrange or rewrite the rest of these spots. So this is 1 bar, 3, 1 bar. Okay. And then you can do the rest of these spots yourself as well. I'll just do a couple more here. Oh, what the heck? I'll do them all here. Not that many of them. So we have 3, 1 bar, 1 bar. Okay, and again, right, all of these spots dot to 0 with B. Okay, you can verify that, just do the math. And then the last one right here. 1, 3 bar, 1. And there you go. Okay, so the zone axis family for this is the 1, 1, 2 family. All right, let's move on here. So we have a body-centered example, okay? And again, right, this has 2 symmetry, and this is your orthogonal G vector pair right here, okay? So once again, oops. Okay, so that is 4.48. Oh, these things are always right in the way. Where is it? And I have 4 divisions. Okay, and then for this guy, I only have 2 divisions. We won't make do anyway. Did I move it? Nope, I didn't. Come on. Come on. Come on. Computer's having a moment here. Come on. Okay, what do we got here? We have, again, this zoom bar is in the way. 5 inches flat, okay? So that's over 2 increments. All right, let's run the routine here. Okay, and we only get 2 hits, okay? First one we can rule out, mathematically does not work, okay? We cannot get a 0 dot product. This one we can though, okay? Very easily, right? We could just have 2, 0, 0 and 0, 2, 4 and we would be fine, okay? So let's assign the indices as that, okay? So we will call, let me move these, let me move our arrows out of the way here. Oops, I already have that there. Okay. Okay, so we end up with the closest. Okay, so that is 2, 0, 0. And 0, 2, 4. Okay, oops. Right, and then 2, 0, 0 cross 0, 2, 4 gives us our out of page direction. Okay, or we could have put this down here, and that would also, right, that would also be valid to do that. Okay, it's going to give us a different answer for B. It's going to change the sense, but that would be perfectly valid. So if we're doing it this way, because this is how we've been doing it, longer cross shorter. So we have 0, 2, 4 cross 2, 0, 0. Right. So we have 0, 0, 2, 4 cross 2, 0, 0. Okay, B solve. Okay, and so we get the zone axis as 0 to 1 bar. Okay, 0 to 1 bar. And we can verify that the dot products all work and go to 0. So my zone axis family is 0, 1, 2 here. Okay, kind of an odd one, right? But you know, sometimes this happens. Okay, you end up with, you know, results like this. All right, so we want to index some of the spots. That one is the opposite. That's the opposite. That's 2, 2 bar, 4, 4 bar. Come on. That's 2, 2, 4. Okay, and those spots in the middle are half. Nope. What are you doing? I don't want help. Okay, 1, 1, 2. One, one, oops, sorry. 1, 1 bar, 2 bar. All right, I'll do a couple more here. Okay, so we can see, right, all my equidistant spots again, same family, right? So now if we wanted to rearrange this with the soft rules, this would be 0, 1, 2. Okay, so this would still work, right? I could leave this as 2, 0, 0. And then if I do, so if I do 2, 0, 0 cross 0, 0 cross B, I point down here, so then I can reassign this. Okay, so well, I go ahead and do that. So we come back here. Okay, so we have 2, 0, 0 cross 0, 2, 1. Yes, so it's giving me 0, 2 bar 4. Okay. And then from there, right, it's just a bunch of vector math. Okay, if you want to, I'll just do these closest spots in the vicinity here. So this guy would be 2, 2 bar 4. And this would be 1, 1 bar 2. Okay, and then that would be the opposite, that would be the opposite, so on and so forth. Okay, all right. So we got one more example here. Okay, and I saved this one for last deliberately because this is the cat daddy of them all here. This is what I like to say. This is the most studied zone axis by TEM ever. Okay, this is the 110 family zone axis for diamond cubic. Okay, and specifically as studied for silicon. Okay, although again, right, the way I've been doing these simulations, I've just been, doing them for just some nondescript structure. Okay, but any diamond cubic structure, the zone axis for this would look the same. Okay, all right, so you can see some interesting things. First of all, so there's actually some holes here, right? So we're seeing, right, like inside these rings, there's actually some spots missing, okay, which is kind of odd, right? You would think, right, based on the arrangement, you probably see a spot here and here, but we don't, okay? So there's actually a good reason for that, which we'll get into here in a minute, okay? The other thing too, okay, it might be tempting if we had a spot here to think that this was actually 6 mm symmetry, but it's not, okay? You have to measure carefully to verify that, but you could actually show that you don't have that symmetry, and this is 2 mm symmetry, okay? So again, don't just, take a cursory glance and assume the symmetry is what you think it is, right? Some of these, they're a little more, what's the word? It's a little finer, a little more scrutiny than you would think, okay, to verify that it has a certain symmetry, okay? So this is the shortest G vector, right? Here's my two orthogonal G vectors right here. Okay, so I end up with 3.17 divided by 2. And I also have 2 increments for this guy. What do I get? I get 4.43 divided by 2. Okay, so let's run the solve and see what we get. dp solve. Whoops, and now we have to tell it. Oh, you know what? When I did this last thing, I didn't switch it to body center. Let me let me switch this here and make sure. It should give us the same answer here. Okay. Let me go back and change this to the ratio we had at 5 and. Okay. So let me go ahead here. Okay. Let me switch this. I forgot to switch this to BCC for the last example. All right. We should get the same answer though. That should be the right answer. dp solve cubic. Okay, yeah, so it does give us the same thing, okay? It gave us a red herring here again for the first one, but again, you cannot mathematically get these to dot to 0, okay? And you can for these. So the only difference, right, was the other possible pair that may have solved. Again, I'm talking about this example that we just did for body-centered cubic. I forgot to change the crystal to BCC. So I went back and did, right? I knew the solution was what it was, but yeah, but I wanted to make sure that it actually worked right, okay? Yes, so yes, again, you can't get these to dot to 0 and you can for these, okay? All right, so now that we've made sure that we didn't introduce a catastrophe here, let me go ahead here and reset these. So now we're going to do diamond cubic. So we make sure that's good. Okay, and let me go back here now this guy. Okay, so R1 is 3.17. Come on. Two increments. And R2 is 4.43, two increments. All right, let's run it. Okay, so it's only giving me one solution here. So the way I have this coded is that if there's only one hit, it only gives me that answer out. Okay, so there's only one reasonable solution here. And we can see, right, very quickly that yes, this does dot to zero. Okay, we can get a mathematically acceptable arrangement. Okay, but let's just look through the table anyway. So it's giving us this ratio. So really nothing there. Right here, we're close. Okay, but the rest of these, yeah, there's really not a good match here, here, here. Okay, so yes, so this is saying the second G vector for G1 and the fourth G vector for G2. And yes, 0, 0, 2 and 0, 0, 4. And yep, I know those are the correct HKL families. So let's assign G1 as 2, 2, 0 and G2 as 0, 0, 4. Okay, so we'll go ahead here. Zero, zero, 4. 2, 2, 0. Move that out of the way. Okay. And so then if we do 0, 0, 4 cross 2, 2, 0, okay, B solve. Yes. So we get the right family. We get 1 bar, 1, 0. Okay. So our zone axis family is 1, 1, 0, right? The most studied zone axis ever. Forgive me for a second. I need to just step away for just a minute here. Go ahead and mute the mic for a second. Okay, I'm back. Yeah, sorry. Wasn't counting on the video going this long, but yeah, I had to run to the restroom there for a second. All right, so let's do some math here, okay? So now, I'm sorry for the scrolling here. Okay, this gets a little trickier because we don't have the spot here, but I assure you it's still not too bad. So this guy right here is 2, 2, 4. Okay, and now we have to be a little creative here. Okay, so there would be a spot, a 0, 0, 2 spot here, but there isn't. Okay, so right, this spot would be half of this spot, but this spot also isn't here. So this spot would be 2, 2, 2 right here. Okay, so then what that means is that this spot has to be 1, 1, 1. Okay, so yeah, the absence, the little holes in this kind of make this a little tricky. So then if we add, okay, if we add half of this G vector to this, we get this. Okay, so half of this is 0, 0, 2 plus 1, 1, 1 is 1, 1, 3. Okay, right? And then from here, pretty straightforward. That's, of course, all the opposite indices. And yes, again, I maintain that this is the most technologically important and studied zone axis ever by TEM, is the 110 family for silicon. If you do any work with the physical sciences, you will encounter this zone axis at some point in your career, I assure you. And I encounter this basically, if not every day, probably every week in some capacity. All right, so let's do a few more here. How about this guy right here? So the slides that you're seeing, these are actually taken from a course that I taught, how many years ago was it? 5 years ago, on TEM. So I did a whole graduate course on TEM, and so I had these slides already prepared. So it was fairly easy to kind of put all this together. All right, so what do we got here? So then this is 0, 2, 2. So this would be 2 bar or 1 bar, 1 bar, 1 right here. Okay, and that's 1, 1, 1 bar. Okay, so you can see my equidistant spots are all in the same family, right? Just like I would expect. And again, we can also see I'm getting 0 dot product with B for all of my indices as well. Let's do a couple more here. Okay, so this is this plus 0, 0, 2, so that's -1, -1, 3. Okay, and then I'll do one more over here, since that's its opposite. Okay, so now the holes that we see here, okay, we don't see 0, 0, 2 and 2, 2, 2 because, again, they're not kinematically allowed, right? They're not in the list here, okay? So they're what's called kinematically forbidden. However, when you are observing this pattern experimentally, very often you will end up seeing these spots anyway, okay? You'll end up seeing them anyway because of a phenomenon known as double diffraction, okay? So without going into too much detail, double diffraction is basically where you have a sample that's, it doesn't have to be necessarily very thick, but it's strongly diffracting, okay? Although having a thicker sample will help. And basically, you have a Bragg beam serve as an incident, like an incident beam, to create another diffraction pattern, okay? So that's called double diffraction, right? Where you diffract once by the Bragg beam and then you diffract again, okay? So to show you how this works, right, give you kind of a extra lesson here. So I'm going to copy this pattern here, and then I'm going to make it transparent so you can see. So let's assume right here, okay, let's assume that this spot where my mouse is, this one, actually, let's use 1, 1, 1 since that's easier. Let's assume that this is strongly diffracting, and this serves as an incident beam. If I shift the whole pattern up and superimpose it on the other pattern, my holes get filled in. Okay, my holes get filled in, and now I actually see these spots that are kinematically forbidden. Okay, so that's what double diffraction is. And more than likely, unless you are dealing with a really, really thin sample, you are probably going to see those spots in your DP if you're dealing with a diamond cubic crystal. If you're dealing with zinc blende or face center cubic, you will see them regardless because those are kinematically allowed in both of those crystals. Okay. Okay, so anyways, that's why we don't see those, right? But it's very striking, right, to see this compared to the other ones where we didn't have these big holes. All right, so if we want to apply the soft rules, we rearrange this as 0, 1, 1, okay? And let's rearrange this guy to be 4, 0, 0. And then we do, if we do B cross 4, 0, 0, that points this way. So let me go back here. Okay, so we do 1, 1, 1 cross 1, 1, 0, sorry, cross 4. Oh, sorry, my bad again. 0, 1, 1 cross 4, 0, 0. And I get, okay, and then I reduce this down to 0, 2, 2 bar. So this is 0, 2. What's going on? 0, 2, 2 bar. Okay, all right, so let's rearrange or redo some of these spots here. So this guy would now be 4, 2, 2 bar. This is 2, 0, 0. So this would be, I believe that is correct. 2, 2, yes, that is correct. Okay, so then this spot would be 3, 1, 1 bar. Okay, all right, and then from there, let's go ahead and do the rest of these. Since we'll do it in honor of this hurricane, which has thankfully not been terrible here. I did get a text message saying that we are allowed to go back to work tomorrow. So this is then the opposite there. This is the opposite there. Okay, and then this is 4 bar. Did I fix that one already? Looks like I did. 3 bar plus 2 bar. Yep, I guess that works. Okay, all right, so then this spot here would be 2 bar, 2, 2 bar. So this is 1 bar, 1, 1 bar. And then this is 1, 1 bar, 1. Okay, this is 0, 2 bar, 2. This is 4, 2 bar, 2. And do I have the right number here? So that would be 2, 2 bar, 2. Okay, so this is correct. And I think all of these are otherwise correct. Okay, I think we're good. All right, let me do these other ones out here, just, for the sake of cleanliness here, since we're finishing this up, just to make everything look nice. Okay, and then one more out here. And there we go, okay? So you can verify, right? I get a 0 dot product with all of these indices with B. Sorry, let me get out of this, okay? So that holds. Although, wait a second here. Now I've got some funny business. Okay, this spot is not correct. No, this spot is not correct either. What's going on here? That should be 4. You guys let me do that. So that's 3, 0, 0. Okay, so this should be 2, 1 bar, 1, 3, 1 bar, 1, and this should be 3, 3 bar, 1, 1 bar. Okay. Yes, these are all correct now. Okay, I realized that didn't dot to 0, and it should have. All right. We should be good to go here now. Everything else looks okay. Yep, we're good to go, right? You could do the rest of these out here as well if you wanted to, all right? So that is the crash course in in indexing cubic diffraction patterns. So now if I get ambitious, I may do one for hexagonal. Okay, so you can do, if your material is hexagonal close packed or has an A to C ratio that is close to the ideal hexagonal close pack ratio, you can also do that in a manner that is similar to how we do the cubic ones, although to be sure, it is definitely more involved. Okay, so that might be another video. Okay, but I know there was a lot of interest in do a video about indexing, you know, diffraction patterns and figuring out the zone axis. So long time coming, but we finally got it done. So all right. So with that, I will get this up as soon as possible, and I look forward to doing some more videos. And again, thank you so much for all the support, and please feel free to like, share, and subscribe, and look forward to seeing you all again soon. All right, thank you.